So, let us get to the differences between the simple homonuclear diatomics and the heteronuclear diatomics. The first thing is, for a heteroatom like Hx, if you have to write, or Xy if it does not involve hydrogen, what is important is that the 1s orbitals, the 2s, 2p etc. of the H atom have different energies compared to the 1s orbital, 2s orbital, 2p orbitals of the X atom. And we already have a way of defining qualitatively what is called the electronegativity, which is the ability of the atom to retain the electrons more closely to itself. It is a measure. The electronegativity scale tells us that if the X atom is more electronegative, it also means that the corresponding energy levels, the same 1s of H or 1s of X, this will be lower in energy, this will be higher in energy. Likewise, the 2s electron for the Hx of H will be higher in energy than the 2s electron energy level of the X atom. These are all again approximate energy level classifications. Therefore, if for example, let us take carbon monoxide as an example. Carbon, there are 6 electrons for the carbon, 4 valence electrons, and in the case of oxygen 8 electrons, and essentially if you include the 2s and 2p, there are 6 valence electrons. Okay. But we will generally not worry about this 2, write 4 if we have to, but it does not matter. So, if you draw the energy level diagram for the carbon, (2s) if we write C and oxygen here, and if you write the 2s energy level for carbon, then you would see that the corresponding oxygen 2s would be lower if this is the increasing direction in energy. Therefore, what you would see is that the 2s sigma, which is of course lower than the energies of either the carbon 2s or the oxygen 2s, and the sigma star 2s is slightly lower than the 2s energy of carbon, but much higher than the oxygen. So, you see that this is sigma 2s, this is sigma star 2s. Okay. And since there are 2 electrons in both carbon and oxygen 2s, we will have all 4 filled up here. Okay. Now, on the 2p, there are 3 2p orbitals again here, and 3 2p orbitals for the oxygen. They are again lower in energy, and you can see that the carbon monoxide being stable, net stability essentially gives you that these are the pi orbital, and then you have the pz sigma orbital. So, this is pi 2p x, pi 2p y, and this one is sigma 2p z, where z is the axis for the carbon oxygen bond. Therefore, now you have the remaining, there are 4 already here, and the remaining 6 electrons that you have to put in are here. Okay. We have started with only 2s, therefore, we are not considering the 6 electrons as a starting point. We will only take 4, the valence electrons, and the 6 valence electrons here, including the 2s orbital. So, you have a total of 10 electrons, 2, 2, 2, 2, 2, 2. This is the energy level diagram for the molecular orbitals of carbon monoxide approximately. Then the same thing can be done for nitric oxide, NO, and you can see that in the case of nitrogen again, the 2s orbital of the nitrogen is higher than the 2s orbital of the oxygen, and so you can see that there is a slight increase for the sigma star and a lot decrease in the sigma 2s, sigma star 2s. So, another important factor. Anyway, let me finish this and then we will write the other important consideration. This is for the nitrogen. There are 4 valence for carbon, and for nitrogen we have 5 valence for carbon, for nitrogen here. Let me see, there are 5 valence electrons for nitrogen and 6 valence electrons for oxygen, leaving the 1s out. And if we have 3 p orbitals here, but the 2 p orbitals for nitrogen and the 2 p orbitals for oxygen lower in energy, then you can see that this is the pi 2 p, and this is the sigma 2 p. And these are pi 2 px, pi 2 py, and the anti-bonding orbitals are all, of course, they are that. Okay. Now, you can see that the NO has the 11 electrons distributed this way with 1 electron here on the anti-bonding orbital, paramagnetic. So, this is another, but what is another important factor is that when we write the NO, the bonding orbital, for example, for the 2 p, if we write the psi MO bonding C1 times the 2 p orbital for nitrogen plus C2 the 2 p orbital for Z orbital for oxygen, because if we do this, you would see that for the bonding case, this is higher in energy, this is lower in energy. You will see that the absolute value of C1 square is less than the absolute value of C2 square. What it means is that the probability that the electrons in the molecular orbital are closer to the or more in the 2 p orbital of the oxygen, that probability is given by C2 square, and that is greater than the C1 square. It is the opposite if you were to write the molecular orbital for the anti-bonding orbital. In that case, the C1 square will be greater than the C2 square, okay, plus or minus if you do that. The bonding combination is a plus combination, the anti-bonding. So, let me take the minus sign out of this and write the minus sign here, C1 phi 2 p nitrogen minus C2 phi 2 p oxygen, if you do that. Okay. With some normalization, of course, this is normalized. You can see that the anti-bonding combination, the electrons are more likely to be closer to nitrogen than to the oxygen. This is a general trend that you see, is another important factor. And also this tells you qualitatively that if, for example, an atom like HCl is to be expressed in molecular orbital combination, assuming that we can locate only one pz or p orbital of Cl and so on, you would see the phi 2p 2s sorry phi 1s of hydrogen, which is way higher in energy than the chlorine 2 p orbitals, the coefficient C1 plus C2 if you put phi, this is for hydrogen, and if you put the 2 p for chlorine, you would see that the C1 square is much less than C2 square for the bonding orbital, meaning that the electrons are more likely to be in the chlorine, the orbital, and therefore the contribution of the chlorine 2 p orbital to the bonding is much more than the contribution of the 1s orbital of hydrogen to HCl. So, this is the other important issue that you have to worry about in the heteronuclear system, that the orbital energies have to be properly assigned. And you realize by this time that when you have so many electrons, this idea of having s and p electrons as separate and higher in energy or lower in energy is also somewhat an approximate picture. The best picture would be to actually see what is the real combination, linear combination by a numerical procedure, and modern computational quantum chemistry of course gives you very accurately the molecular orbital energies in clear increasing levels, and you can see that how the electrons are occupied, and this allows you to calculate the gap between the highest occupied molecular orbital and the lowest unoccupied molecular orbital, leading to what is known as the HOMO-LUMO gap. Highest occupied molecular orbital and the lowest unoccupied molecular orbital. If you go back to these pictures, you can see them right away. For example, in the case of CO, the highest occupied molecular orbital is the sigma 2pz, and the unoccupied molecular orbitals are the pi 2p star, pi star 2py, and then you have the sigma 2pz star. This is the lowest. This is the lowest unoccupied molecular orbital, LUMO, and this is the highest occupied molecular orbital, the HOMO. And likewise, this is the HOMO, and this is the LUMO. So, you can see that this is another quantity that can be calculated, and modern computational chemistry programs calculate this very precisely and very accurately by taking into account a large number of linear combinations of atomic orbitals, not even the hydrogen like orbitals, but by using some other functions which are very comfortable in and easy to calculate, known as the Gaussian orbitals. The Gaussian orbitals are not real or not even close to the atomic structure and the exponential type orbitals that we are familiar with from the Slater model and from the hydrogen model. However, the computational process now takes into account the easiest and the most efficient way of calculating them, because orbitals by themselves do not have a physical representation or interpretation except in taking very precise linear combinations for larger bonding cases, as we do in organic chemistry. It is the square of the atomic orbital and the electron density which is more a physical representation, and therefore finally that is what is important for understanding the atomic structure, the molecular structure in this case. So, this is a very brief introduction to the heteronuclear and the homonuclear diatomic molecule, and let me just close this with again a brief description of what is called the hybridization.